Welcome to the tutorial on security and privacy in distributed optimization and learning. My name is Nitin Vaidya. I'm at the Georgetown University in Washington, DC. Before I get started, let me note that I will make slides of this tutorial as well as videos available online, and you can find them on this website. Go to this website, follow the link for talks. It's a tab near the top of the screen, and then you can find the materials on this website. So this is a very short outline for the whole tutorial. The focus of the tutorial is on optimization with machine learning as being an application of optimization. And in particular, we will look at cost functions that have this structure shown on the top of the slide, sigma fi of x. I'll explain what these things mean, but this is the type of cost function that we are trying to optimize in this in the discussion that we will have in the next few hours. We will consider two different architectures to solve this problem distributedly. In one architecture shown on the left, here the nodes of the agents in the system form a network, a peer-to-peer network, and they collaborate with each other to solve this distributed computing problem. They do not rely on any central entity such as a server for that purpose. On the other hand, on the right-hand side, the architecture is server-based. Server is an entity that all the agents can communicate with, and those agents will collaborate with each other through the server. And there may be even multiple servers in some settings. But these are the two architectures that we will look at when we discuss distributed optimization. And then we will look at the privacy and security aspects in the context of this particular problem for both the architectures. Now, machine learning is a special case of optimization, and we will talk about that as well as we get started. So today, in the first lecture, I'm going to introduce the problem of distributed optimization first, but later the rest of the talk, the first hour or so, will be focused on centralized version of the optimization solution, namely gradient descent. But once we get through the background, then we will talk about distributed optimization. So what's the objective of the problem we are trying to solve? Let me illustrate that with an example. Actually, I will take three examples. So in this first example, imagine that you have three people, three agents who want to meet somewhere. And here I have shown these three people on the map, or actually a picture. And they happen to be, in various places on this terrain, and they want to find a place to meet. And the question is, how do you choose the right place to meet? And so there may be more than one way to solve this problem of meeting or rendezvous. One way to do that, that is of interest for this tutorial, is to define a cost function. So for example, let's suppose the agent in the top left corner is agent number 1 or user number 1. And that agent has a cost function f1 of x. 1 is the index of the agent, and x is the argument, which is the location or a potential location where we might meet. And so f1x is the cost for agent 1 to go from where they are right now to a location x. And f2x is the cost for agent 2, and f3x is the cost for agent 3. And to determine which location to choose, one possible approach is to pick a location that minimizes the total cost over all the agents. So cost here could be time. For example, if somebody has to walk from top of that hill to a meeting point, it will take them a bit of time to come there. Or if you're in a city, then maybe you can take a cab, and it could be the cab fare. Cost can represent different things depending on the context. But then the goal is to minimize the total cost or pick a location where the total cost is minimized. And so this is just a shorthand for that statement at the top. So goal is to compute argmin of summation of fix over all agents I. So the index for the summation is I, over which in this example will be I equal to 1, 2, and 3. And the cost function we care about is the summation. In particular, in this example, f1x plus f2x plus f3x. And what we are trying to find is the argmin, which is a shorthand for argument x that minimizes this global or sum cost function, summation of cost functions of individual agents. So that's our objective, to compute this argument that minimizes the cost function, or to compute the argument. In general, the problem might be constrained, whereas in the first expression here, the subscript x for argmin doesn't specify a constraint. So which is to say, we are willing to meet at any location at all, so long as the sum or the total cost is minimized at that location. Whereas in this slightly modified version of the problem, the subscript for argmin says lowercase x, which is the argument, must belong to this set uppercase x. What is uppercase x? It's a constraint. For example, in this problem, we might say, we don't really want to meet on top of a hill. We must meet near the bottom where the restaurants are. And so we might specify that the meeting point has to be in this region. And that could be my definition of set X. And so that's the constraint optimization problem. And sometimes we focus on optimization with constraints, sometimes it's without constraints. Now, in my slides, sometimes I might ignore, rather neglect to specify whether the problem is constrained or unconstrained, just to simplify life a little bit in terms of preparing slides. And similarly, I'm omitting the subscript here on the summation as well, but hopefully these will be clear from the context. Now let us consider this example of linear regression. What you see in this slide is data points shown in green. Each data point consists of a pair of AI, YI pair. AI in this example is a real number. In general, it might be a vector, and YI is a real number as well. And these points in this particular slide, in fact, do belong to a straight line. But what we do not know a priori is the line, the equation of the line itself, or the parameters for this particular line. Later, we will see that in general, the points that we start with may not actually neatly belong to a straight line. There may be some noise, but we will get to the noisy case in a couple minutes. So the goal again is, given these data points, identify this line to which these points belong. And maybe the equation of the line looks something like this. Perhaps yi equal to 0.5 ai plus 1, or some other values instead of half and 1 there. But suppose that's the true equation for the data that we have. One way to rewrite that equality is to say that yi is the product of the row vector ai1 with the column vector 0.51. And we will find this view of writing yi useful in the upcoming slides. We are going to use this notation ai, uppercase A subscript I, as a shorthand for this row vector ai comma 1. And we will use this again to define a matrix called A. But again, just to recap, we have these points yi or data points yi, and we want to identify the line that goes through all the data points. One can write all the data in this matrix form, where x is now a column vector of, in this case, dimension 2. The actual value of x in our example will end up being 0.5 and 1. But in general, a priori do not know what x is, and x is what we want to compute. We want to compute the value of x, in this case, a vector of dimension 2 that satisfies this equality for all the data points that we have. We are going to denote this matrix as A. Each row of this matrix A will be denoted as uppercase A subscript I for the ith row. And X again is a column vector, in this case of dimension 2. Now we want to solve for X, but if you take any one of these equations for any one data point, such as y1 equal to a1x, then there may not be a unique X for which this equality is satisfied. There may be more than one possible X for which the equality is satisfied in general, because the dimension of X in this case is, in the example I'm showing on this slide, is actually 3, and all you have is one equation here. One value of yi is known, and we cannot actually unambiguously determine the vector x. I should have probably labeled this as x bracket 1, x bracket 2, because later on I use subscript for x as a time index. But here it's just the element, here in this slide, xi is just the ith element of vector x. So the goal for linear regression is that given y and y is a column vector, a is a matrix, determine x such that y equal to ax. This vector x is going to be a d-dimensional vector in general. In my example, first example, d was equal to 2, and we will view that as a column vector generally. And so A is a matrix with some number of rows, let's say n rows and d columns. And we will need the matrix to have sufficient rank for us to be able to solve this problem in the sense of finding a unique value of x, which we will call x star as the unique solution of this problem. So x star will basically be the parameters of this line that fits this data that we have. Now, I'm sure some of you have seen these problems before. It's just solving a bunch of simultaneous equations in these variables that are collectively called vector x. But an alternate way to think about the problem is as distributed linear regression, and we will define a cost function that corresponds to the problem formulation we have here. So again, each agent I knows some data. We are going to assume for now that each agent knows a single data point. The ith agent knows ith data point yi equal to aix. So the agent knows yi and ai. It doesn't know x. That satisfies the x star, the unique solution of the problem. The agent I doesn't know a priori. But hopefully collectively all the agents can collaborate and find the x star that satisfies this equality for all I, for all the agents. And so that's the goal of distributed version of linear regression, that this agent should collaborate somehow to solve this problem. One way to do that is to define these cost functions. So for agent I, we are going to define this cost function fi of x, where fi of x is defined as yi minus aix squared. Now, in the event that x is equal to x star, because we are assuming in this example that the data actually belongs to a straight line, we know that for a particular x equal to x star, yi will be equal to ai x star for all I. And therefore, this will be equal to 0 for all I, as long as there is such a unique x star that exists. And obviously, the minimum value of fix over all x will be 0 as well, because we know it's 0 at x equal to x star. But in general, if you just take any one of these cost functions, fix, then of course the argument of fix is going to be not unique. It will contain x star as a possible solution, but there will be other possible x as well that might satisfy, that will minimize the cost fix individually for a given particular I. But if these agents collaborate together and minimize this cost function, which is a summation of all the local cost functions of various agents, and then we try to find the argument that minimizes that cost, so long as that matrix has the right properties, we should be able to find this unique x star that satisfies all those constraints, yi equal to aix. And so one way to solve the problem that we started with is actually to solve this optimization problem, which is analogous to the rendezvous problem we saw earlier. The difference is that the cost function here and the cost function there were not the same, but finally the structure of the problem is comparable. And what we're going to care about eventually is that the functions that we are solving for, rather functions we're trying to minimize, have this structure where each agent has its own cost function, and what we care about is minimizing the aggregate over all the local cost functions of those agents. In general, like I said earlier, the data may be noisy. Maybe it doesn't belong to a straight line perfectly, but maybe you can fit a straight line well enough. And this may happen if there is some kind of noise in the system. So these yi observations are linearly related to A, but there is a noise. And so in general, the equation may look like this: yi equal to ai x star. There exists an x star such that this is true. The agent only knows ai yi. and the agent needs to estimate X star, or rather the agents collectively need to estimate X star. And the solution will be similar. We look at this function as before and try to minimize this. And hopefully this gives you a good estimate of X star. And that will happen if the noise is not very large. Okay, so that's linear regression. And yet another example perhaps is machine learning. And there are many such examples, by the way, of cost functions of the form that we're looking at here from many different domains, in fact. But in machine learning, let's say you're trying to train a neural network or something like that. Then you have this data. Let's say we're training a classifier. Then you have this data, for example, this is a data set of images, and they're classified as cars, birds, things like that, boats. And depending on what machine you're training, the problem formulation, the exact formulation might look slightly different. But let's say it's a neural network. The bottom picture there shows neural network. Now, so what you have been given is a set of data pairs. Each data pair is the data, in this case, an image, and yi is the class. So for example, the image may be a bird, a picture of a bird, and the class will be a bird. For example, in this case, the data itself is this particular picture, which I took some years back. And the class in this case is a cat, right? Because we have a bunch of cats in this picture. And so what we have been given is this kind of data set. And the goal is to determine a neural network that will classify this data or data of this kind well, whatever that well might mean. So you can think of what this neural network is doing is to take input dj, and then it's implementing a function y to compute a label for this data. And what we hope is that the label that this function computes is actually equal to yj, and if not equal to yj, close to yj, right, in general. Just the way we saw for linear regression, we may not be able to fit the line exactly on the points, but we want something that approximates those points well. So y is the function that is implemented by the neural network. And if the neural network does not map these points very well, meaning if for data item j doesn't produce yj exactly, and in general it won't, there are reasons that you don't want to do this, because you want the network to be able to classify other data as well. But in general, these will not match. Sometimes that's desirable, in fact. But then we'll define the so-called loss function that measures how well the data is data that is available, in this case, dj yj pairs, is classified by the neural network. And we, in practice, would do this not just on the training data, but we also want to do it on some other additional data. We want to measure how well the neural network classifies the data on which it was not trained, actually. And here is a cost function, an example of a cost function. So in this case, ydj is the function that the neural network implements. dj, if you apply an input dj as an image, then the output of the classifier, let's call it uppercase y of dj, this thing here, yj is the desired output, and the difference between them, and if y is a scalar, then I just take a square. Otherwise, I can take the square of the norm, L2 norm, and I'll explain in a minute what L2 norm is. But you can define a particular cost function. The exact nature of the cost function is, again, not too critical for us, but just know that you can design a cost function, and the goal then is to minimize the cost function as a way of measuring how well the network maps the data into a class. Okay, so we are going to define the so-called loss for each data item that we care about. So we may have a set of data items that we want to classify, or we want to test the neural network on a set of data item. And for each of those items, we define this cost function Lj, where j is the index of the data item in that particular set. Now, during training in a distributed setting, what may happen is that what we are aiming to do as we train the network is to minimize this cost over the training data. Now, if the data in general in the distributed system will be distributed, and in a centralized setting, the data is all in one place. So in the centralized setting, what we care about is to minimize this loss over all the data items on which we are training, right? At least we want to make it small, and then we will verify how the network does on the test data. But during training, what the training process is essentially trying to reduce this cost, the loss in general. The loss itself is so-called cost in my context, all right? And so this is what we're going for. We may not actually get to the true minimum. We might stop before we reach the minimum itself as we train. But in general, the context of the presentation today is that we have this global cost, which in this case, this is the global cost, and we're trying to minimize this. How close to the minimum we get depends on the context. How close to the minimum we try to get depends on the context. In the distributed setting, though, nobody has all the data. So for example, in this picture, there are 4 agents and the data is distributed. These agents could be, for example, hospitals, where each hospital has its own data set, or each agent could be a cell phone. For example, on my cell phone, when I type stuff on my keyboard, there may be, the system may be collecting my keystrokes to train a classifier to say, what am I typing, for example, or try to predict what the next thing I'm going to type. But the data is distributed because of the way the system is built. And then the question is, can you use all that data that is distributed to train a neural network collaboratively? One way to do that, of course, is to bring all the data in one place. But we are not aiming to do that. We want to keep the data where it is, and yet try to collaborate to train a neural network somehow. So now what we are going to consider is the fact that each of these agents, like this guy in the bottom right, agent number 4, has only part of the data. So I'm going to define a cost function for agent I, or in this case, agent 4. That's the cost function, where X now represents the argument that I'm trying to compute. But for a neural network, that X is a vector of the weights and biases in that neural network. And how do I define Fi of X? It's just the loss, summation of the loss over all the data items that are available to agent 4. So again, the data set on which I'm training is distributed, and agent number I has part of the data, and we're going to call that on this slide, the data set that agent I has is DI, D uppercase D subscript I. And so the cost corresponding to agent I is just the summation of the loss over all the data items that are available locally to agent I. Now, what we really want to do when we train the network is not to minimize any one of these cost functions. We want to minimize the total cost over all the agents, just like we did in a centralized setting. And therefore, what we're really doing is trying to minimize the global cost, the sigma Fi of X. We want to find the argument that minimizes this cost, which is to say, I want to find in the neural network setting all the weights and so on that minimize the cost function, or at least make it small. And that's what I'm doing when I train the neural network. Okay, so that's just background to say that these kinds of questions are interesting, where you have a bunch of agents and each agent knows its own cost function. This is all they know. They don't know the cost functions of other agents unless they talk to them. And in general, we're looking at a setting where you don't actually want to share the actual cost functions with each other, but you might share some other information as a way of collaborating with each other in order to solve this particular problem. Like I said before, this particular formulation appears in many different settings beyond machine learning. And so there has been many decades of work on this problem, in fact. The machine learning setting has become somewhat more popular lately, but researchers have been looking at this distributed optimization problem for much longer than that. So in this tutorial, we will assume that the functions are convex and then discuss algorithms for minimizing such functions. In today's talk, we will assume, or rather we will discuss only centralized algorithms for minimizing convex functions. But later we will get to distributed algorithms as well. But first, just very briefly, a couple of properties of convex functions. What this slide shows actually is a definition of convex functions. In this illustration, the argument x is a scalar. And what this inequality at the top says is that if you take 2 points, x1 and x2, 2 arguments, x1 and x2, and interpolate between them to obtain x3, like here, then the function value at x3, which is the left-hand side of this inequality, is less than equal to the corresponding value here, which is on the right-hand side of this inequality. Okay? That's just the definition of convex functions. The next slide shows another inequality that is useful in the proofs. We will just focus on this one, this version of it, this implication of it just briefly. If you plot those two vectors, the left-hand side is a product of these two vectors, and the right, they're lower bounded by 0, which is to say they're positive. So one way to think about it is that this vector x star, x to x star, and the vector that is pointing in the negative gradient direction, they make acute angle. We won't be using pictures like this, of course, to prove anything, but we will be using inequalities like this in deriving correctness of the algorithms. In fact, we won't even cover the proofs in this tutorial very much, but if you look at the proofs in the publications, they use inequalities of this sort to prove correctness and convergence risk claims and so on. Here is another equality that holds for convex functions. This product on the left is lower bounded by 0, so that product is non-negative for any convex function that is smooth. I should have said that I'm assuming that the convex functions we're dealing with are smooth, which is why the gradients exist. In cases where gradients don't exist, if the functions are not smooth, then sometimes you can use subgradients instead of gradients, but we won't discuss non-smooth functions in this tutorial. For strongly convex functions, on the left, on the previous slide, we had a 0 instead of this term. If you go back here, so we had a 0 there on the right-hand side. And here now for strongly convex functions, the 0 is replaced by this quantity where beta is positive. And functions that satisfy this constraint are said to be strongly convex. Where the right-hand side, this term here depicts a norm, which is just the length of that vector y minus x, defined as here. We will refer to functions that meet this property with for a given parameter beta to be the beta strongly convex functions. We'll very soon refer to functions that have Lipschitz continuous gradients, and this is what it means. If the function has a Lipschitz continuous gradient, then this quantity on the left is bounded by, upper bounded by this quantity, u times the norm of y minus x. And functions of this sort, we will refer to them as mu smooth. Mu is the parameter on the right-hand side. And these gradients are said to be Lipschitz continuous. The reason the gradients are Lipschitz continuous is because on the left-hand side, we have the difference of gradients at y and x. If the function is Lipschitz continuous, and on the left-hand side, we'll get the difference between the function values at y and x. And the right-hand side looks similar to the earlier inequality. And for some algorithms to show correctness or convergence claims, some of these assumptions are made, either Lipschitz function, continuous function, or Lipschitz continuous gradient. Like I said earlier, we assume that the gradients exist. And if the gradients, if the function is non-smooth, then sometimes you can design algorithms that use subgradients instead of gradients. Here is a very simple example of computing gradients. In this example, let's suppose a vector x consists of two elements u and v, and the function is 4u squared plus 2vq plus 5. And to find the gradient, we first take partial derivatives of the function with respect to u and v, and those partial derivatives are shown here. And then the gradient is simply a vector that contains these two partial derivatives, del f del u and del f over del v. And this is the gradient that we obtained at point x equal to u comma v. Again, in general, we are going to treat the argument x to be a column vector, so the gradient will be a column vector as well. And that's why I have written a transpose here. Sometimes I might forget to write down the transpose in my slides, but you should be able to figure out when the transpose is supposed to be there. In general, we may not work with closed form equations for the function. Instead, we may have to use our alternative methods. For example, in neural networks, uh, the, the function is represented by the neural network itself, and the, the vector x is the parameter vector for the neural network consisting of the weights and biases. And to compute the gradient, we need to compute all these partial derivatives with respect to the weights and biases. And the so-called back-propagation algorithm is actually achieving exactly that. It is computing the gradient. Now, if you don't know what back-propagation is, that's all right. In the rest of the talk, we will just assume that we know how to compute these gradients. We won't have to actually compute them numerically or any amount of detail in my presentation here. Okay, let's discuss how we can minimize convex functions. And the algorithm we're going to use is a gradient-based algorithm, gradient descent or gradient method. And the basic principle here is that wherever we are in this space of parameter x, we can use the gradient to decide which way to move so as to decrease the function value. And so we are going to start the algorithm at some location x that may be chosen arbitrarily here at the top right corner of this curve. So in this curve, the vertical axis is the function value and the horizontal plane is the parameter x. So it's a two-dimensional parameter x. Now, we start at x0, we compute gradient f of f at x0. And the gradient method will have us move in a direction that is opposite the gradient. And that's how we get from x0 to x1. And then we'll get from x1 to x2 as I will show you on the next slide. So the iteration in general looks like this, but in particular, we will compute x1 to be equal to x0 minus the gradient at x0, except that we won't just take the gradient by itself, we're going to multiply it by a quantity, lambda 0, which is called the step size, okay? And the step size can be chosen in a variety of ways, but it's just a number. It multiplies the gradient, a positive number. Now, similarly, we'll compute x2. So we'll start from x0 to x, we'll get to x1. And to go from x1 to x2, we do the same thing. This is the step we are going to take next. X2 will be computed as x1, which is where we are, minus the gradient of f at x1. But again, we'll multiply by this quantity, lambda 1, which is the step size, and so on. So this can continue. You go from x2 to x3, from x3 to x4, and so on, always moving in the direction opposite of the gradient. It's opposite because we have a minus sign here. The step size can be chosen to be a constant. In some algorithms it is time dependent. For example, it might be chosen as lambda k equal to 1 over k plus 1. In some algorithms, it is chosen as 1 over square root of k plus 1. And in some cases, lambda k may actually depend on xk itself. So lambda k is a step size that will determine the property of the algorithm, in particular the convergence rate, as we will see later. But once you choose the step sizes correctly, this algorithm can be shown to converge to the minimum, the global minimum of the convex cost function. Okay, so what I want to give you are some very quick summary of some convergence claims for these kinds of algorithms. Again, this talk is about distributed optimization, but I thought I should mention some results just so you get a feel for what these algorithms look like. And the convergence claims for different algorithms are for different quantities often, but this is what they are for. So sometimes the claims are about this difference. So fx star, where x star is an argmin of the function fx. Fx star is the minimum possible cost for the cost function. And this is really the difference of the cost at x equal to xk and x equal to x star. If xk were to be equal to x star, this difference would be 0, and smaller is better, right? So you want to make this small, or this could be what we are trying to bound or give the convergence on is the distance between xk and x star, which is to say how far are you from the true minimum of the cost function. and maybe we care about the L2 norm of this distance. So that's another, in some cases, the results are bounding this difference. And in yet another case, you have results that bound this difference. So what is this? Here we are looking at the difference between the current argument value xk and the true minimum. Whereas here we are looking at not just the current value, but average over the history, right? You're starting from the initial, maybe this should be t equal to 0, from the initial value to the current value, and then k equal to k plus 1. Yeah, okay, but the average over all the estimates so far, not just the current estimate. And some algorithms will use, so some proofs will use this measure as opposed to this measure, depending on the context. So I'm not going to be always very precise about these, but just know that the claims are not all about the same quantity. Okay, so we're talking about algorithms that look like this for the most part. And by convergence, what we're really asking is how quickly do we get close to the optimum, right? Can we say something about these convergence rates? And the answer is yes. For many of these algorithms, there are well-known results, but the results vary, and they depend on many things. So the results may depend on, is the function just convex, or is it strongly convex function? Is the function smooth, or is the function not smooth? Are the gradients Lipschitz? Are the gradients not Lipschitz? I haven't discussed what stochastic gradient is yet. I'll talk about that soon today. And it also depends on the choice of the step size. Is the step size constant? Is it time varying? If it is time varying, exactly how does it change? So all of those affect the convergence claims. And I'm not going to dwell on any of these in any great detail today, but let me just quickly go through some of the claims. So here is one possible outcome you find for some algorithms where this gap is shrinking very rapidly. So it's shrinking as c to the k, where c is a fraction. So if c is a fraction, as k increases, c to the k goes to 0 very quickly, right? It goes very rapidly. If this is what happens, then the convergence is said to be linear, or sometimes, depending on who you talk to, they might call it geometric, depending on the community. The reason it is said to be linear is that if you take the log of this, then you get something, it's upper bounded by a linear function in k. So that's how I interpret the linear part of it. But I find this actually a more meaningful jargon. But the point is that it's very fast. The gap goes to 0 very quickly. And this happens, for example, for strongly convex functions under some assumptions about lambda, k, and whether the function is smooth and so on. Okay, so these details we don't need to dwell on here. But like I said before, the choice of the cost functions matters, whether you get this fast, really fast convergence or not. In other cases, the convergence is slower or sublinear. For example, order of 1 over k, where k is the iteration index. If you remember, if the functions are convex but not strongly convex, then for a step size that is chosen carefully, if the functions are mu smooth or the gradients are Lipschitz continuous with parameter mu, then with this particular choice of cost function, we can achieve these kinds of convergence rates. So it is, as k increases, this gap shrinks, but it's not nearly as fast as the previous slide. Excuse me. And you can find similar results in other settings as well. There is a line of work that is called accelerated methods. Nesterov Acceleration is such a method where if you look at the algorithm, it actually looks slightly different. This step looks kind of like what we had before. If I replace this z by x, then this is exactly the algorithm we had previously. But this accelerated method does something different. It is computing this intermediate variable zk as a function of the current value of xk and the previous one. And so essentially there's some history here that is incorporated in computing zk. And then we use that value of zk to compute the gradient and then take the step. But this particular modification looks very simple on the face of it, but it improves the convergence rate from 1 over k to 1 over k squared. So it's a significant benefit by without really much more work. We are just keeping a little bit of history during the computations. And again, we won't look at why this happens. I just wanted to point out that the convergence rates vary. Under some assumptions, other assumptions, you get convergence rates that look like 1 over square root k as well. And when we talk about distributed optimization, we will come back to these convergence rates again. And you can compare and contrast with the rates you saw on these slides later. So I want to mention stochastic gradient method a little bit in somewhat more detail, because a lot of the work on fault tolerant or secure machine learning uses the stochastic method. So if you recall, the iteration that we looked at until now looked like this. Okay, we are computing the new value of x, xk plus 1, as xk minus lambda k and the gradient at xk. So we are at xk right now. We'll take a step in the direction opposite of the gradient at the current value of the xk, and the step length is determined by this lambda k parameter. The stochastic gradient method actually, instead of using the actual gradient itself, it uses, in effect, an approximation of the gradient that I'm calling here g of xk. But the g of xk is such that the expected value of the gradient, of the stochastic gradient, is exactly equal to the true gradient at xk. Okay, so I may not be using this gradient itself, but on average, right, the expectation of the gradient I am using, the stochastic gradient, is in fact equal to the true gradient. Okay, this is the kind of gradient we are using in these algorithms. And this algorithm actually does converge as well under the right set of assumptions. It can get to the minimum or close to the minimum. So here is an example of stochastic gradient method. So let's look at cost functions of the kind that we discussed earlier. F of x equal to summation of fix over different agents I. And what we are going to do in this particular setting to implement a stochastic gradient method is to be going to pick, suppose if I comes from the, let's say this set 1 to 10, meaning there are 10 agents, I equal to 1 to 10. And I'm going to pick an arbitrary, I'm going to pick a value ik in kth iteration of the algorithm, such that the value ik is chosen uniformly at random from the set 1 to 10. Right? So maybe we pick ik equal to 4, in which case the gradient that I'm going to use here is going to be, so g x4 is going to be equal to the gradient of function 4, because I happen to pick I equal to 4 at that value. In the next round, when I equal to 5, again, I toss a coin, pick I randomly. Maybe I happen to choose 10 this time. Then the gradient I'll pick will be at 10. Okay, you get the idea, right? So I'm never computing this gradient, because this gradient will be equal to the gradient of the summation of all these gradients. Okay, I'm not computing the summation ever. I'm just computing one of these gradients in each round. But over time, as you can imagine, because I'm choosing I randomly, eventually I'm going to sample each possible value of I with equal frequency, right, over long enough intervals. And that helps, that uniform distribution here allows us to essentially approximate this gradient over short time intervals. Any given round, right? For example, the gradient of f, what was it now? 4 was it? Actually, these numbers happen to coincide, so maybe I should, let's suppose I4 happens to be 5, then I would have chosen the gradient of function f5 at x4, okay? Now the difference between that gradient and the gradient of the full cost function, right, the summation at x4, these two may be very different, in fact, because this term here is a summation over all the gradients of all the agents, whereas the term at the top is just one gradient. They may not at all be like each other in general, but some under the right assumptions, this algorithm will converge close to the true minimum. And so intuitively, why does that happen? Or first of all, why am I even doing this, right? If I have all the agents, why don't I actually compute the gradient of this whole cost function anyway? Intuitively, what is going on is that if you have if the number of agents is very large, millions, billions, right? If you're thinking of each agent to be a cell phone, you could have an enormously large number of devices. Or you may have, if each I represents one data item, then you will again potentially have a very large number of data items to compute the gradient on. So each iteration is very cheap now because you're doing much less work than computing the full gradient. So here is what's going on pictorially. In this example, I have defined a particular cost function. So think of U1, U2, and U3 as your data items. These are just points in space. And the cost function fi of x is just the distance between x and ui. Okay, so just the distance between x and this data point, the ith data point, is what I'm defining as the cost here. That's what this says. So if x happens to be here, then the gradient will basically take you towards the ith point. In this example here, the gradient, if it is the cost function f1, then my gradient will want me to, you're trying to reduce the cost, you just go towards the, if you follow the gradient descent step with just on just f1x, then you'll move towards u1. That's how you want to move. On the other hand, if you are doing u2, or if you're taking just the cost of function corresponding to data item u2, then when you take the gradient descent step, it will move you towards u2, right? And with the stochastic gradient method, that's what you're basically doing. You're moving actually in the opposite direction of the gradient of each of the individual cost functions. So in round number one, maybe I should have written actually minus here, shouldn't I? Yeah. So I'm going to move against the opposite direction of the gradient corresponding to cost function one. In second round, I moved I was here to begin with, then I'll move in this direction a little bit, depending on my step size. And so it so happens that I move there. So I'm here now. In the next round, the gradient I use happens to correspond to this data point U2. Then I'm going to move in this direction. How far I go depends on my step size again. But let's say you move to here, and in round number 3, you're going to move towards the other data point, and so on. And you'll keep doing this. And the claim is that, of course, you could have started somewhere far away, by the way, and moved here and so on. But the claim is that eventually you get close to the true minimum somehow. So now in this example, one thing we could observe is that we have a lot of data points here. Each of them defines one of these cost functions, fix. And I have colored those data points here in green, red, and blue just to make an observation. So what we're trying to minimize is the total cost over all the cost functions, so all the agents, or in this example, the sum of the distances from all these points. And perhaps the optimal x star is somewhere here. Okay, this may be the x star. Let me draw it with, let's say yellow. Can you see yellow color? Yeah, maybe that's where the x star is. But what you might observe is that if you minimize the cost over just the red points, you might get something like this X I had drawn in yellow color. Now, clearly the global minimum is not quite the same as this minimum over just the red points, but they're close enough. And if your data has redundancy in the sense that to compute X star, the argmin for the global cost, approximately, it suffices to use a subset of the cost functions, then the stochastic gradient method might be a win, because whereas the exact gradient method will compute the gradient of all the component cost functions, the stochastic gradient just computes one at a time or a small number of gradients at a time, And before when you look at all the cost functions, you might be able to take a step in the right direction because of this property that only a subset of the cost functions are sufficient to make progress towards the optimal or sufficient to actually compute the minimum approximately. And in many applications, the data tends to have this kind of redundancy. So stochastic gradient can be a win, partly because, of course, the gradient computation is fast. We're only computing some of the gradients in each iteration, but also it naturally exploits the redundancy. The downside, though, is that there is some variance associated with stochastic gradients. An extreme example of that would be when, imagine that we are at, I should change the pen color here to, let's say, this one. Suppose we happen to be at x equal to x star, meaning suppose this is the minimum, the optimal point. If you look at the exact gradient of the sum of the cost function sigma fix, that gradient is going to be 0 at the minimum of this global cost function. However, if you look at the individual gradients of each of these component cost functions, right, f1x, f2x, and f3x, those are actually not equal to 0. And so the exact gradient is a constant 0, whereas the stochastic gradient, even at x equal to x star, if you draw different values of I, you're going to compute a different stochastic gradient, and so the variance actually is non-zero. And so this variance of the gradient in the stochastic method results in slower convergence time. And there are ways to mitigate that. For example, you could use something called the variance reduction techniques to try to essentially reduce the variance of the stochastic gradient. Or one, instead of, in my example, I said that the stochastic gradient, the way I obtained that was by picking a random value ik, and then I compared the gradient of this function fik. That's what I did, of one function. An alternative is to do something more general, where in the kth round or kth iteration, I pick a set of indices. So it could be ik1, ik2, ik3. In this case, I pick 3 different indices. And then I'm going to compute the gradient of these 3 functions and use the aggregate of those 3 gradients. So I'm using aggregate of 3 gradients instead of just 1. And so this is the so-called mini batch approach. The more gradients I use in a given iteration, the less the variance will be, intuitively speaking. In the limit, you can use all the functions, and of course, then you get the exact gradient. But in between the 2 extremes, you can have more than one function chosen in a given iteration to try to reduce the variance. And there are other ways of doing this as well. But by and large, stochastic gradient may perform slower because of the higher variance. And many of the correctness claims for the stochastic gradient method will make assumptions about the variance of the stochastic gradient. And we might come back and talk about that later on. So there is this very nice paper that provides a survey of some of these convex optimization methods that you might be interested in. There are, of course, other papers and even books on these topics that you could look at. And I will try to provide pointers to a few more of those later on. We're going to now transition to discussing distributed optimizations in the next video.